This next section of the notes deals with the terminology that is associated with all trig graphs. So you need to be aware of the word amplitude and know that amplitude by definition is the maximum distance from the mean position or the middle of the wave. Both the sine and cosine curves have an amplitude of 1 because we know that their values from 0, and the mean value is usually 0. They're never more than 1 unit away, so they're +1 or -1, both of them. And when we look more generally at trig equations in the format y = a sine x, for example, or y = a cos of, and I'll talk about b in a moment, x. So we're just really focusing on the a, the number in front of the sine or the cos ratio, then the amplitude will change to a, because we know that the sine of an angle, this part, can never be bigger than 1, and if we're multiplying any of those values by a, the biggest value you'll get will be a times 1, which is a. The other terminology that you need to be familiar with is the word period. And it says here, well, the 6 trig functions are all periodic because they repeat themselves over and over again. And the period then is the length of the smallest repeating interval. You might note that. The length of the smallest repeating interval. Hopefully you've graphed enough trig functions now to know that the period of sine, cosine, cosec and sec functions is 2 pi. You've got to cover a total of 2 pi before the pattern repeats itself. The period for tan, though, and cot is only pi. So you can check this out using your graphs. So you know that the tan function has, or the tan graph has this repeating shape, and we're going from -pi on 2 to pi on 2, which is a total of pi units. And from pi on 2 to 3 pi on 2 is 2 pi on 2, which is pi units. You can see the period is pi units, the same with cot. I briefly touched on the impact of putting a number directly in here in front of the x and seeing how that impacted on the graph, and we know that putting a value in there, either a number greater than 1 or a fraction, results in a graph being stretched or compressed. And if it's stretched or compressed, it's affecting the period. So it says this obviously impacts on the period. Please take note, the periods, so sine, cos, sec and cosec have period 2 pi. These also have periods 2 pi on b. Introducing a b in here makes the period smaller. And unless, of course, that's a fraction, because if you divide by a fraction, it's the same as multiplying by the fraction inverted, so it would extend the period. Tan is normally pi. Introducing a b in front of the x, it has has this impact in that it's pi divided by b on the period. The graphs of the trig functions support many other translations that you are already aware of. We know that, for example, algebraically we found this in the previous trig chapter, that sine of 90 minus x is equal to the cos of x. Just think for a moment about the graph of sine of x or sine of 90 minus x. We know that impacting directly here on the x is going to translate it. And we know that the only difference between sine and cos is that cos has been pushed over, is the equivalent of the sine graph being pushed over. So you see some nice supporting concepts, both graphically and algebraically in our understanding, when we develop our understanding of the graphs for trig ratios. We've looked previously at the symmetry of curves, and we can see that the sine curve has rotational symmetry about the origin. If you rotate it, then it simply repeats itself. So it has rotational symmetry. Therefore, it is an odd function, and if it's an odd function, it has this property. Likewise, we can actually see demonstrated in the graph that if you were graphing sine of x plus 2 pi, then you're translating it 2 pi units backwards. But we would know that if we took our original graph, our sine curve here, which under normal circumstances is over 2 pi, and pushed it back 2 pi, then we're getting this graph, which actually goes on to be exactly the same. We know also that sine of x plus 2 pi, so think about it, we're going around our quadrant, we're here at 2 pi, we add on x degrees, and we know that that is the same as the sine of x here in this first quadrant. So the sine of x, or 2 pi plus x, is the same as the sine of x. So algebraically, we write this. It's supported graphically by understanding the translation and the values of sine x in our quadrant format. The graphs nicely support all of these conditions, that the sine of minus x is minus the sine of x, so you can see here if we're at pi on 2, the sine of pi on 2 is 1, and the sine of minus pi on 2, the sine of minus pi on 2 would be minus 1. There's lots to go through there, and I'm not going to just repeat all of those here on the video. You will need to become familiar with them, and hopefully that's enough for you to be able to do exercise 14C.